group 2 for the thermocouple time constant experiment. So what is the thermal time constant? The exact definition is right there. The time required for a thermistor to change is 63.2% of the total difference between its initial and final body temperature, subjected to a step function change in temperature under zero power conditions. So essentially what I took away from that is it's how long it takes to change ambient temperatures. Generally, things that can affect time constant are larger sizes of the thermistor assembly. That's probably the main one, but other things such as thermal conductivity, mass, surface area to mass, they can all affect it too. So to do the calculations for this experiment, we had to use the lump capacitance method. So in order for this to be valid, the assumption needs to be made that the thermal system has no internal thermal gradients. And then by doing a balance between the rate of heat that is convected from or to the system and the rate of change of the thermal energy in the system, we get that first equation there. When you integrate both sides, taking an initial condition T naught at time equals 0, get that second one there. And then above your E value right there, next to the negative T is what your time constant would be equal to, as you can see in equation 3. Now when you substitute 3 into 2, and you take the logarithm, the natural logarithm both times, you get that equation, which can be rearranged into this. The glory of that equation is that you can actually use that by graphing time against the right side of that equation to find the time constant as the slope, negative tau. So these are my initial results when you just take raw temperature versus time. At the top is the insertion and the removal of the ice water, or into and out of the ice water, and then down here is the insertion and removal from the boiling water. So then this is normalized temperature versus time. So this is before you take the natural log of it. So as you saw earlier in that equation, there was a T, which is your time at the specified, or your temperature at the specified time. T naught, which is your temperature at the initial time, and T infinity is your ambient temperature. So for water, ambient temperature, ice water, I use 0 degrees, boiling water, 100 degrees, and then in air, when it's being removed, just at about 22 degrees. That's about room temperature in Celsius. Yes, so now here, that's what I was talking to you about earlier.
Yeah, you were right, by the way.
I was? Okay, cool. So, by plotting the natural log of the normalized temperature, can you go back actually to that equation? So, here we can see that this is going to be your independent variable in this equation, realistically. I mean, time is almost never independent, but in order to situate the equation correctly to find the correct value for tau, you're going to want to put this along your x-axis and that along your y-axis. All right, go back. Thank you. So that, when you do that, you end up getting negative tau. So you can see by putting a best curve linear fit. Now, I didn't cancel out the noise because I've never done this before and I didn't know that existed. So some of mine are a little less linear than they could be. But from this equation, the slope is going to be your time constant. So now, these are the results I gathered. And from these results, I'd say that, so the ice water ones make sense to me, but the boiling water ones don't. Question marks. Yeah. So let me explain why. You can actually go to the next slide. So a smaller time constant is supposed to yield a faster thermal response. So by that logic, when you think about, so liquids have a greater heat capacity than air. So basically, the insertion, go back for me. The insertion should always be lower, whether or not it's boiling or cold, because of the fact that the liquids have the greater heat capacity. So it should basically always be faster, which means the time constant should always be smaller, which you can see here in the ice water, but then the boiling water is flipped. And I have no idea why, I gotta be honest. There's either a discrepancy somewhere in my calculations, but I checked it a couple times and I couldn't find it. And in the actual experiment itself, our group and another group were responsible for putting it into ice water. So I never actually got to see the boiling water experiment happen. So I'm not sure where to find that discrepancy. You can go back forward. No, not back, forward, sorry. But yeah, so based off of that, yeah, I think the time constants for the first one were right. I don't know how large they should be, but yeah, you can go next. That's about all I got for you guys. Does anybody have any questions for me?